the study of electric flux. It is another term which we need to know the meaning of it, and also the importance of the flux. What is the meaning of electric flux? Here, if we visualize, just visualize some surface area, some area which is of course two-dimensional. Area is a two-dimensional. In the electric field, this is the usual representation of electric field. That is a series of parallel lines with a direction. This is electric field. If the area like this is placed in the electric field, the electric field pass through the area. The amount of electric field pass through that area. The measure, that is the measure of electric field pass through the area is called as flux. What magnitude of electric field passes through or flowing through that given area is called as electric flux. In terms of electric lines of force, electric field lines like this, we can define it as number of such lines, electric lines intercepts with a given area. It is also called as flux, that is eta. Symbolic representation of flux is eta. Correct definition for electric flux is a mathematical definition. What is that mathematical definition? That is flux, electric flux is equal to E into A into cos theta. E is, it is electric field strength, electric field, and A means area through which that electric field is passing through. This is a vector and this is also a vector. And cos theta, I'll tell you what is cos theta. That is electric field into area of a vector. Area is also a vector. Because just to understand, that is area about the vector, let me recall the vector mathematics again, but it doesn't require over here. So this is a geometry we require to define or to show that area is a vector. This is three-dimensional. You can call it as x direction. This is y direction. This is z direction. Three coordinates axis. And if a vector like this, A is a vector, is along the x axis, and B is a vector, that is small b is a vector along the y axis. Of course, it has both magnitude and direction. This is the direction of the vector. Magnitude is the length of this. It also has both magnitude and direction. And these two lines or these two vectors are subtended by the angle alpha, some angle alpha. When you multiply these two vectors, A into B, you get what is that? A vector known as area. Area is a vector. That is A into B is another vector. That is the area vector. Therefore, it is a cross product. Area is a cross product. This is the angle between these two vectors. Now, it is a magnitude of the vector. Area has some magnitude. Magnitude is what is that? This length into this length gives the magnitude of the area. What would be the direction of that vector, area vector? The direction of the area vector, this is in this plane, the area. The direction of the vector is what is that? Along the z axis, and it is away from the plane. That is, it is perpendicular to the plane. this z is perpendicular to the plane and the direction is away from the plane. That is the direction of the vector. What vector? Area vector. This is the direction of the area vector. That is a mathematical representation of what is that area, vector area. It has both direction and magnitude. It is only a magnitude of the area. That is mathematical representation of the magnitude of the area, and it is a vector, area vector, mathematical representation of area vector. So now we understand, if you have any plane, the area of the vector and its direction, what is that, is always perpendicular to the plane. Any surface area, the area vector direction is always perpendicular to the direction of the, that is perpendicular to the plane and away from the plane. That is the direction, like this. So just to understand, area is a vector. This doesn't require over here. Now let us come back to the mathematical representation of electric flux. That is eta is equal to, that is E, magnitude of the electric field. A means magnitude of the area, because that area has some magnitude, that is area. And into cos theta. What is theta? The angle between the two vectors, because there are two vectors, vector E, vector A. That is, vector A direction is always normal to the plane. Normal is perpendicular to the plane. So this is perpendicular to the plane of the surface. And it is placed in the electric lines like this. So this is the direction of the electric field, this is the direction of the area vector. Maybe different or same. It depends on what is that alignment of the plane with the line. So this vector into this vector, when you multiply these two vectors, you get a what is that known as flux. The flux is scalar. That is why this vector product is a dot product or scalar product. So scalar product, definition of scalar product is this into cos of the theta. What is theta? Angle subtended by these two vectors. So that is a mathematical definition. So this flux, that is the flux depends on this and this. I have the value, I have the value, I have the value, I have the value. And also for a given value of E and E, it also depends on the angle theta. Depends on the angle theta. For the given value of E and A. For what is that? Some value of E, that is fixed, some value of A. So this value oscillates between, that is the maximum and minimum. That is flux is equal to E into A. That is the maximum value when theta equals 0. Theta equals 0 means that is the direction of the area vector and the direction of the electric field vector remains same. It is same when this area is exactly perpendicular to the direction of the electric field like this. That is, if the plane is like this, the normal or direction of the area is, this is the direction of the area. So this is already direction of the electric field. This is the direction of the what is that area vector. Both are same. That is theta equals 0. Cos 0 is equal to 1. So we get what is just multiplying these two. Maximum value for a given value of E and A. And the value is minimum is 0 when theta is equal to 90 degree. Theta equals 90 degree means when this surface is exactly what is that in the plane of the electric lines. That is, if the electric lines are in the board, plane of the board, this area or this area surface also is the same, that is in the same plane, that is board plane. So if that is the case, the area vector is perpendicular to the board. This is in that is the angle between this vector and this vector is equal to 90 degree. This plane and the plane of the electric lines are the same, coincided. Then the angle between the area vector and this is 90 degree. For 90 degree, theta equals 0. That is cos theta cos 90 equals 0. So 0 into this is 0. The possible value of flux, that is no electric lines passing through this. Electric lines passes only when they are like what is that with certain angle or exactly maximum when it is perpendicular to the direction of the electric field. So this is the magnitude of the flux. So equation for this correct mathematical definition for electric flux represents or measure what amount of electric field actually flowing through the given surface. It is called as electric flux. So this is the mathematical definition. The same thing, it can be represented in differential form or differential equation. That is the same thing. What is that? We can take any point on the surface. This is usually electric lines of forces. Direction of the electric field. Any point and the area at the point is taken as what is that? Area is infinitesimal area. Infinitesimal is small. If this is area is what is that? A. Then what is flux? Flux also infinitesimally small. Infinitesimal value. The D, that is eta is equal to, this is electric lines of force. So this into this equal cos it is, if it is differential function, this also differential function. That is a differential equation. So for what is that? The entire surface, that is flux through entire surface, we need to integrate the differential equation. Integration on the left hand side, integration on the right hand side. This becomes, so this is a constant. This is the integration of this is and constant. Integration of this dA is equal to A. That is the integral equation. So straight away what is that? Defined with integral equation. This is differential representation. Why we represent differential equations? Because this is the one usually we commence with for the derivation purpose. This equation, derivation always commences with this differential equation and end up at the integral form. That is why differential equation is also important. That is about the flux. That is surface and electric lines. How many electric lines pass through surface? That is a flux. So that is a surface area. If this surface area, the most important thing, if this surface area is enclosed, that is enclosed into what is a certain space inside, that is enclosed surface. Example, geometry of the enclosed surface are this. These are geometry of open surfaces. If you have surfaces means there are mainly two different surfaces, open surfaces and enclosed surfaces, that is closed surfaces. These are the geometrical shape of closed surfaces. That is spherical shape all around inside space. That is closed surface. There are 6 surfaces are there, closed inside space. This is cubical shape. Of course, any other shape. I have mentioned only some of the closed surfaces. This is another closed surface. That is cylindrical shape. That is surface cylindrical shape sideway, and up is also that is closed by circular surface. So up and down are closed. That is closed cylindrical surface. So among the open surfaces, I will give some examples. That is what is a rectangular planar. It is not closed. Maybe circular planar shape. And it is what is again half of this closed spherical means hemisphere, open. The surface is open. Here cylindrical. This is closed, but these two openings are not closed. Upper and it is open cylinder. So if they are closed one or both, it is open always. Open cylindrical surfaces. So these are the things I'm talking about. What is that? If the surface is enclosed into any shape, if the surface is enclosed into any shape with certain space inside, that is most important one, no hole or no opening, and the space inside contains some amount of charge, electric charges. It may be positive or negative. So what happens? The space inside some charge is present. What will happen? It is exact. What is that? What is that called? Electric field. Electric field direction. What is that? The field direction may be what is that? Away from this space or towards this space, inside this space. It may be what is that? Like this spherical closed surface. Away because of positive charge, towards electric lines or electric field towards this space because of minus q. And this is what is that? Entire surface area through which what is that? Electric lines are passing or electric field is passing through, and total electric flux, that is total electric flux, electric lines, electric field, and the total surface, that is total surface of the enclosed surface. So when I talk about the electric flux due to this is always equal to what is that? That is Q divided by epsilon naught. What is Q? Amount of electric charge enclosed in that enclosed surface divided by epsilon naught. What is epsilon naught? It is the permittivity of the free space. Permittivity of the free space. So this is known as Gauss theorem. It has been proved that. So that is the meaning of flux with respect to any surface. If the surface is enclosed with certain amount of charge, that total electric flux by the entire surface is exactly equals to Q divided by epsilon naught. Q is the amount of charge enclosed. It is known as Gauss theorem. That is the representation. What is that? Electric lines of force direction away from the space where the charges are enclosed is towards the space where charges are enclosed by this spherical surface. It is the one applicable for, need not for any spherical shape, applicable for any kind of shape or any shape, enclosed shape. And this surface is called as Gaussian surface. Remember the term, the meaning of Gaussian surface. What is Gaussian surface? Gaussian surface, that is enclosed surface. So this equation, what is called? This equation is applicable for that Gaussian surface. Q divided by epsilon naught. It is the amount, total amount of flux is equal to Q divided by epsilon naught for any Gaussian surface, which is enclosed surface, enclosing some amount of electric charge. This is about the statement of the Gauss theorem. We shall have to, if you say anything, what is that the statement, we have to prove that. What is the proof for the Gauss theorem? Let us take some spherical, some enclosed surface. I am taking this enclosed surface here, spherical shape. The spherical shape has radius, R is the radius of the spherical sphere. Let Q is the amount of charge enclosed in it, that is plus Q. That is a numerous amount of charges, plus charges. So it is enclosed in this space, and that is entire surface, total what is a spherical shape. Let me take any point on the surface. At this point, what is the electric field? Because this charge exerts electric field. So direction of the electric field is this. It is moving away from the charge. That is the direction. That is electric field at this point is E. And at this point, what is that point I have taken? The area. What is the area now? That area is dA. That is the direction. That is the direction, area direction. And this is the direction of electric field. Mathematical equation for this infinitesimal equation. That is, this is the one we are using for differential. Differential function is the one we are using for this point on the surface. That is a differential function of the flux is equal to E into differential of area into cos theta. But one thing is very important. If you take any point, that any infinitesimal area, that direction of the area vector and the electric field vector directions remain same or coincided. That is theta is equal to 0. This is a spherical surface. You can consider any point on the spherical surface. Any point on the spherical surface, this holds true, theta equals 0. This line and this line always coincided. The direction of the area vector, electric vector coincided. Therefore, it is reduced to this. And this upon integration, this integration is called, what is that? This symbol is only for a plane like this, surface like this. So now you have to give a special integral sign. This integral of this is circle. What is that? Circle represent Gaussian surface. That means this equation for the Gaussian surface. This is a Gaussian surface, enclosed surface. It represent enclosed surface. So that is a flux of the enclosed surface is equal to integral of this E into dA, total surface area of that enclosed geometry. Geometry is here. So E into A. So that is the mathematical final equation for this. The flux due to this cube with that through the entire surface, that is surface area of the total spherical surface area of this A. So which you know that mathematical definition for the area of the total spherical surface is 4 pi r square. R is the radius of this sphere. And E, you have to write the definition for E for any point. Just recall the mathematical definition for E at any point is equal to Coulomb's constant into, that is Q, amount of charge enclosed in it. Let us say that it concentrated at this point at the center Q. The distance between this and this is R square. So mathematical definition for electric field at any point is equal to this at this point. So put this and this into this equation and simplify. Let us see what we get. So that is flux eta is equal to, this is E, this is A. Here R square cancel and K is there, Coulomb's constant. Substitute for Coulomb's constant. What is that? That is 1 by 4 pi epsilon naught. Put this also into this equation and simplify further. That is Q divided by, that is 4 pi epsilon naught into 4 pi. So 4 pi cancel, remaining is Q by epsilon naught. That is flux is equal to Q divided by epsilon naught. Look at the theorem what I stated. Theorem what I have stated is Q by epsilon naught for any Gaussian surface. This is a Gaussian surface of this shape. So we can also, what is that? It may be of any shape, but final mathematical evaluation comes to this. So it is the total flux by the Gaussian surface is equal to amount of charge enclosed in it divided by epsilon naught. Thus the Gaussian theorem is proved. This is a proof for the Gaussian theorem. This is the statement for the Gaussian theorem. So this is about the Gauss theorem. What is the importance of the Gauss theorem? What is the importance? That is significance of this equation. This equation is called as Gauss theorem. Finds application. That application is, using this we can derive the equation. We can write the mathematical equation for electric field. For electric field at any point. Electric field at any point due to what is that linear charge distribution like this, or electric field at any point due to a surface charge distribution, that is surface area, and also electric field at any point due to what is that volume charge distribution. I told you there are three types of charge distributions, that is numerous charges: linear distribution and surface distribution, volume distribution. So using this finds application, easy way of mathematical evaluation. Easiest way of mathematical evaluation for electric field at any point by those set of electric charges. Either may be linear charge, here only I have shown for only linear charge. So it also for the surface charge and also volume charge as well. So this mathematical easiest way to arrive at electric field. This is one already derived in the previous class using other mathematical methods. Using other mathematical methods. So this is the easiest way. Look at that. This is a linear charge distribution, that is charges are aligned along a line. If you want to find electric field at a point around it, anyway, here or all surrounding that, no, any point, electric field at any point, it is also in the vertical direction to this line, of course, any point. This is a linear charge distribution. This is the point I have taken here, this point. So to find the electric field at this point, we have to draw what is some geometrical shape. Geometrical shape for this Gaussian. So what is that? Geometrical shape to what is that? Suit for the Gaussian surface. That is the geometry I have drawn. That is what is the suitable, what is the Gaussian surface for this line of charge and the point where we need to find out the electric field. That is a geometrical, what is a suitable geometry for this? That is a cylindrical, that is cylindrical shape. That is same radial distance. The point may be here or here. It is at the same distance from the line. The radius, that is radial distance will be same. Cylindrical shape. It is closed. This also what is that? Open is closed. This also closed with a circular plane, with a circular surface. But here the surface is not uniform like this. There are surface, that is shapes are different. It is cylindrical shape, closed. This is circular shape. So in this geometry, that is what is that? Closed surface, that is Gaussian surface, enclosing all these charges, and using this charge we have to find out the point. So keeping the point and this is the possible geometry we can draw. It is called as Gaussian surface. So that is the most important point. First, you have to draw the suitable Gaussian surface for this mathematical evaluation. This is the one suitable one. Now we can find out that is geometry, Gaussian surface. Gaussian surface means that is total surface of this electric flux. Therefore, now there are three different phases. That is, a phase is circular phase. There is one more phase, that is upper phase. That is called cylindrical shape. This is sideways cylindrical shape. That is circular shape. Three different surfaces are there. Let us write them as S1. This is cylindrical shape. S2 is circular shape closing the upper end. S3 is again circular shape of the same size, that is closing the lower end. There are three surfaces. So with this, what is that geometry? Now let us think about what is the direction of the electric field with this line of charges. Remember, the direction of the electric field is always what is that? Perpendicular to this line all around. That is direction of the electric field. Electric field direction, electric field direction, electric field direction, electric field direction. All around this. And electric field is not in this direction, that is it is through this surface, through this all around cylindrical surface, but electric field is not, that is passing through what is the these two surfaces, but in this direction, that is the one. And of course along this line what is the electric field is in this direction is there, but in the same line, what is minus this point. So let us not worry about this one, this surface is very important. And electric field direction is only, this is the direction, and let us that is think about what is the area vector. Area vector is this the direction for this surface. Area vector for this surface is this direction, that is plane surface perpendicular to this surface, that is the one away from this. So the circular surface, of course it is perpendicular to this surface and away from this. That is also perpendicular to this, away from this. That is the area vector for this surface, area vector for this surface, area vector for this surface. And we have to write that is total Gaussian surface, that is total flux. The total flux by this Gaussian surface, there are three surfaces, write three equations. The equation for surface 1, equation for surface 2, equation for surface 3. So equation for surface 1 is this. So at this point, direction of the area vector, direction of the vector remains same. This equation for this equation for this surface, this equation for this surface, because three surfaces for total surface. But remember, these directions are same, that is theta equals 0, theta equals 0 at this point, any point like this, directions are same, therefore the equation agrees to this. But look here, area direct, that is area vector direction electric field vector here perpendicular, here perpendicular, therefore 90 degree, this is 90 degree, this is 90 degree, therefore 90 means cos 90 means 0, 0 into anything is 0, 0. So these two equation, what is that, becomes 0. Finally what is the left now? The total flux by this Gaussian surface, only this equation, that is Gaussian surface. So that is the differential equation. Integral of this gives S1. What is S1? Total spherical surface area of the cylinder, cylindrical shape. So as you know, the total spherical surface, that is final equation is eta is equal to E into S1. S1 is the spherical surface area. The second, the mathematical definition first, definition for this, or mathematical equation for this surface area is 2 pi r L. R is the radius of the cylinder. What is L? Length of the cylinder, same as length of this charge dissipation. That is the surface area of the cylindrical shape, 2 pi r L. Substitute into it. S1 is this E. And substitute for psi. And here also substitute for L in terms of charge density. You have three different densities. Linear charge density. Lambda stands for linear charge density. Charge amount of charge, total amount of charge divided by the total length. If lambda equals this, what is L? L equals Q by lambda. So this L is equal to Q by lambda. Substitute for L in terms of charge density, Q by L. You know. So next in this equation, substitute for what is that eta. What is eta? It is a flux by the Gaussian surface. It is same as Q by epsilon naught. That is what is that? Q by, that is epsilon is eta is equal to Q by epsilon naught. So left hand side is the flux by the Gaussian surface. Into the right hand side is same now. Simplify, or what is that? Solve this equation now. Solve for equation 1. That is Q cancel, and E is equal to cross multiply, you get this value.
that is 2 pi epsilon naught is there. So let us write this in terms of what is the Coulomb's constant. K. What is K? 1 by 4 pi epsilon naught. Here only 2 pi is there. Convert 2 into 4. Multiply the numerator and denominator by 2. 2 by 2. 2 remains, 2 becomes 4. Now it becomes 4 pi epsilon naught. R remains. That is 1 over this is K. 2 lambda K divided by R. The final equation. That is equal to electric field. Electric field is equal to 2K lambda by R. What is electric field? Electric field at this point. The point may be here or here or here or here. Electric field by electric field at any point around this linear charge density. Around this linear charge is equal to 2K lambda by R. R is the distance between the point and the linear charge. It is same as radius of that is cylinder, Gaussian surface. So this equation you have derived in the previous class using alternate mathematical method. But this is the easiest way to arrive at this equation using Gauss theorem. So this is one of the applications of Gauss theorem. Another application, let us see, electric field at a point due to surface charge, one more derivation, and electric field at a point due to volume charge. These are the applications, mathematical derivation for electric field using electric field due to charge distribution, continuous charge distribution. So let us wind up.